team, Rez and Charles and Laura and Amy. And a few logistics. The bathroom is, we walk left here, go down the hall, it's on your right by the elevators. If you haven't signed in, maybe just give us a sign-in before you leave today. And if you're not already on our email address list, just write your email. Otherwise, I already have you on, don't worry about it. Please help yourself to some coffee and donuts. Okay, oh, I do also want to mention that Charles records the lectures, and we are still working on our website. There's some glitches with the website, but if you type in LUCA lectures on YouTube, you'll be able to find the previous lectures as well. Okay. LUCA lectures, L-U-C-A lectures.
It's a YouTube playlist.
YouTube playlist.
So they can go to YouTube and type.
And I will make a note to send that out in the follow-up email. My students know if I don't make a note of it, they worry about it. So today we would like to welcome Professor Marc Zamkotowicz to our LUCA stage. Marc attended Bloomsburg University, where he received his bachelor's degree, and then he went on to Old Dominion University, where he received his master's degree. He has been at RCBC since 2002. He runs the Geospatial Technology Program. He's a departmental chair for the STEM department or division. And then he teaches physical science, geology, and geography. Today he's going to teach us about something that's so familiar to all of us, the oceans. But as we always say, when you come to LUCA lectures, you'll leave a little smarter. And so today we will learn some of the science behind the oceans. So Marc, welcome to our stage. Thank you.
Thank you, everyone. I appreciate you coming today. It's great to see you. And I've been on this stage before, and I always enjoy it. And I love speaking about things that I have a vested interest in. And today it happens to be the oceans. As you can imagine, there's a wealth of information that's out there. So it's hard to touch on every little aspect of the oceans. There's just so much that we can talk about. So I've tried to focus on certain aspects, but if you have questions about other items or things I didn't get a chance to cover, by all means feel free to ask. You can also talk to me after the lecture, and I'll be happy to try to answer any questions that you may have. When it comes to the oceans, my background is actually geology. I do know about the oceans, and one of the things that astounds me all the time is how mysterious they are. As a matter of fact, the initial title is Mysterious Oceans because it turns out that the oceans are constantly revealing new and new things. We are a land-based organism, people, and we feel like we know a lot about the land, and we do. But when it comes to the oceans, we're realizing more and more things all the time. So, to kind of give you an idea, one of the things I want to talk to you about is some of these new ideas and these new revelations that the oceans are giving up about how we perceive our world. But I'm going to begin by taking a look at oh, there you go. So there we are. There's our Earth, right? Nice blue marble. We've got the deep blue of the oceans, the white of the clouds and the ice, and of course the land bodies. This is our home, right? And just a short distance away, a mere 140 million miles, give or take, we have Mars. And Mars leads us to realize a wealth of information about this torn planet. We have craters, we have volcanoes, we have river valleys, sand dunes, sandstorms, polar ice caps, all sorts of amazing things. And if we go a little bit further out, the beauty of Saturn. Saturn and its glorious rings of ice and rock. We have banded surface of Saturn with its hydrogen and helium revealing all sorts of atmospheric conditions about convection cells and currents and all sorts of wondrous things about Saturn. And just a short hop, skip, and jump away, we have about 4.6 billion miles away the icy world of Pluto. Thanks to the New Horizons spacecraft, which arrived at Pluto recently, we have a revelation of Pluto like we've never seen before, this icy covered surface. Again, rift valleys, mountains, icy about Pluto all the time, and this is 4.6 billion miles away. That's pretty far. So, question is, wait a minute, I thought you were talking about the oceans. True. So why are we talking about these things? Well, this kind of is a testament to our revelation and how we perceive our world relative to others. That's the bottom of the ocean. 12,000 feet away, give or take. So here we can see the surface features of an icy world 4.5 billion miles away, but when it comes to the bottom of our area, our very own ocean, we got nothing. So it's amazing at how dramatic the oceans are. And granted, despite our technical capabilities, we can get very good, very precise images of the ocean. It's just that the oceans are so gosh darn big, they're enormous. So the oceans are obviously one of the most notable features we have on the planet. We've been interacting with the oceans for thousands of years, yet they still remain foreign to most people. And an understanding of the oceans are extremely beneficial for a number of reasons. Well, first and foremost, it helps in understanding climate. Climate, I know, is a hot-button topic nowadays. Everybody's talking about climate change, and so forth. The oceans play a critical role in that. We are still learning exactly how, but we know that the oceans are so involved, and we'll be touched on this a little bit more later on. We have new regions and parts of the oceans that have yet to be discovered. We are still learning more and more about the oceans. As far as the oceans go, in terms of mapping, about 5% of the oceans have been mapped across the entire planet, 5%. The technology is sophisticated. We can make very detailed maps of the ocean floor, but like I said, the oceans are so big, it's hard for us to really wrap our heads around all that may be out there. So invariably, there are still certain parts of the oceans that we still have yet to explore and name. And it provides us a clear vision of the world as we see it today. And again, the oceans are revealing secrets all the time that force us to revisualize the planet that we actually live on. Give me an example. Mountains. Tallest mountain in the world? Everest. Yeah, I don't think so. Well, I would put it this way. Everest is the tallest mountain when you measure the mountain from the base. But, technically speaking, it's not the tallest mountain in the world. That would be on the Cape in Hawaii. Now, why is that? Well, a lot of people realize that when we look at the tallest mountain, we almost always assume that elevation is measured from sea level up to the top. And in that case, Mount Everest takes the #1 spot. But if you want to look at the mountain as a whole, you got to measure what's below the ocean surface. And Hawaii is big. I mean, it is big. About 10,000 feet high. Or, 10,000 meters high. That elevation will actually surpass that of Everest. It just so happens that a large part of that island is below the ocean surface. We just don't see it. We don't realize that it's there. How about this? Continents. You think you know what North America looks like? Well, maybe, maybe not. When we look at the continent of North America, we can visualize what North America looks like. But again, there's part of the North American continent that's hidden beneath the oceans themselves. This is a screen from Google Earth, and you can obviously see the continent of North America. There's the Baja Peninsula, there's Florida, New England, Alaska, and so forth. This is how we envision the continent of North America. But what we tend to forget is this light blue color you see right here. That's just off the boundary between the land and the water. That light blue boundary is the continental shelf. And the continental shelf, which is part of the ocean floor, represents part of the continent of North America. It just so happens that that part of the continent of North America is submerged by water. But technically, it's part of the continent. Put it this way, if you're on a charter fishing vessel, maybe you're going out deep sea fishing, you're maybe 20, 30 miles off the coast of New Jersey, out in the Atlantic Ocean. You think, well, 20 miles off the coast of New Jersey, I'm obviously over the Atlantic Ocean. Actually, no. 20 miles out, you're still technically over the continent of North America. It just so happens that that part of North America is completely covered with water. So when we want to measure or we want to visualize the actual outline of North America, we got to actually look at the continental shelf as well. And it would give us a very different idea of what North America actually looks like. The same is true for the other continents as well. Okay, so just a couple of ideas on how we can actually re-perceive our world based upon the presence of the oceans. Now look at the oceans themselves. How many oceans do we have? 7, 5's common answer. Yeah, I'm sorry. No offense. It's one big ocean, right? They're all connected. There's no gates, there's no barriers, there's no fences. It's one big ocean. They all flow from one end to the other. So how many oceans we have? One big one that's interspersed by land masses. Okay, all kidding aside, well, not really, but listen. How many ocean basins do we have? I heard that answer before. 5 is the magic number. A lot of people nowadays have grown up with learning about the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, the Arctic Ocean. That's your big 4. However, a lot of people may or may not realize that there was actually a 5th ocean recently recognized called the Southern Ocean. And of course, here are your oceans. Pacific, Atlantic, Indian, Arctic, and Southern Ocean. The Arctic Ocean is the smallest. It's also the most shallowest. The average depth of our oceans is right around 12 to 13,000 feet, about 2 miles deep or so. The Arctic Ocean is only about 2,500 to 3,000 feet deep, so it's considerably considerably more shallow than the rest of the oceans. A couple things that strike me is the Atlantic Ocean, oddly enough, has a shape that looks eerily similar to that of New Jersey. Purely coincidental. The Southern Ocean was actually just named back in around 2000 because oceanographers had realized that as you go from the Indian, Atlantic, and Pacific southward, right around 50 degrees south latitude, there's a dramatic shift in water characteristics. The water gets much colder, water gets saltier, and there's a complete change in fauna, or the types of life that we find. And this change is so dramatic that oceanographers actually recognize this water, which surrounds Antarctica, as a completely different water body. It's strange because in the past, our oceans have simply been designated based upon their proximity to continents. Right? The Atlantic Ocean is found between the Americas and Africa and Europe. The Indian Ocean is between Africa, Asia, and Australia. Well, now we have a new ocean that's recognized based upon the water characteristics themselves. The Pacific Ocean is big. It is big. It's enormous. By far the largest ocean that we have. The Pacific Ocean is the largest geographic feature that we have on the planet. Today, at this very moment, you could fit every one of the continents together in one big, giant supercontinent, fit it inside the Pacific Ocean, and still have room to spare. It's a big, big body of water. And to show you how big a body of water it is, and by the way, just on the side note, I just found this really interesting. We have, what do you mean? I also teach geography, so I'm a big geographer. I love geographic facts. Point Nemo, and I apologize, I could not find this slide in English. It happens to be in Spanish, I don't know why. But Point Nemo, which is situated right there, there's South America, here's Antarctica, is the most isolated point on the surface of the Earth. I mean, it's out in the middle of nowhere. You're talking about 1,300 miles to the nearest landmass. And those nearest landmasses are, in this case to the north, tiny bits of rock sticking up out of the ocean water, completely uninhabited. So there's nothing there for miles. You're talking about 26 square kilometers of nothing but water. As a matter of fact, if you find yourself in or around Point Nemo, there's a good chance that the nearest human being that will be closest to you are orbiting on the International Space Station. I mean, just think about that. Just imagine that. Here you are at Point Nemo. By the way, there's nothing there but water, so forget about any land. But you can be sitting there at that point, and the nearest person closest to you at this point is in outer space. Mind-blowing. It's just amazing. So, like I said, I teach geography, so I'm a big fan of neat little facts. Okay, so we got through the hard stuff. How many oceans? Yeah, okay. I'm throwing a few curveballs. How about continents? You know this? How many continents do we have? You guys are still willing to give up answers. I love this. Great. 7. I love that answer. Well, let me put it this way. Technically, officially, 7 is correct. But you could make the argument that might be 8. Yeah, I know. Pretty amazing, right? The oceans are revealing all sorts of amazing and fantastic things, including what might be brand new continents. A lot of people don't know where this, but it's out there. So we all know about the big continents, of course, North South America, Africa, Asia, and so forth. But there are a couple out there that have recently been proposed. The first one is New Zealandia. So here's the coast of Australia. There's Tasmania. And there, of course, is New Zealand. And this pink outline represents New Zealandia, which some geologists in Australia are actually proposing as a land would they do this, right? Well, a couple of different reasons. Number one, you can tell quite dramatically that this body, this landmass, rises significantly higher than the surrounding ocean floor itself. So it's really kind of standing up kind of like a pedestal above the rest of the ocean floor. Very unique. Also, when we take a look at the rock that makes up this landmass, the rock that we find, even in the oceans, is more reminiscent of continental rock than it is oceanic rock. So, based upon that evidence, a couple of geologists were actually proposing that this actually might be in the continent, New Zealand.
Oh.
Crazy, right? What about another one? Sure, throw another one out there. How about Mauritius? Here's the east coast of Africa, there's Madagascar. In the Indian Ocean, we have the Mascarene Plateau. And this landmass right here has an incredible abundance of zircon and other minerals very commonly found on continental-based rocks. So the presence, or the excessive presence of zircon and other minerals commonly found on continental rocks have led some scientists to suggest that this might also represent a continent or continental fragment of some kind that lies out there in the ocean. Now, first and foremost, I want to impress this upon you. These features have not been officially recognized as continents. They have not. But there is a proposal out there that says that they might actually be. After more debate, after more discussion, scientific inquiry, who knows? You know, future kids may grow up learning about 9 continents instead of 7. So here, not only do we have ocean basins and the most isolated point of the planet, but we actually potentially have a couple new continents out there as well. Okay, so a little bit of geographic trivia for you. Now, what about composition? Well, what's the composition of the ocean water? This is not a trick. All right. What's that brick house made of? Oh, what's the ocean water made of? Ocean water. Yes, water, about 97.5%. But anybody who's dove into a lake and accidentally left their mouth gaping open knows that there's more than just water that's out there. So we also include about 3.5% salts and gases. Now, salts I have in quotation marks because when we think about salt, we think of sodium chloride, table salt. But salts can actually represent any type of dissolved material within water. So that's why I use the quotation marks. And a number of gases. To find out what type of salts we have, there you go. There's your recipe for ocean water, if you choose to make some of your own. So sodium chloride, table salt, of course, about 24 grams. This is within a 1,000 gram solution. A little bit of magnesium chloride, about 5 grams. Sodium sulfate, about 4 grams. Calcium chloride, I don't really know where you get this stuff, by the way. A little bit of potassium bromide, a sprinkling of hydrogen borate, and a dash of sodium fluoride. Yum, right? So that's your recipe for ocean water. Or you can just take a jug and head down to the ocean and eat water. So this kind of gives you an idea about what ocean water is actually made of. And we also have a number of gases. Being a scientist looking at the Earth, the types of things that I really kind of think about when we're at the beach is, when you're at the beach and you're looking over the vast, beautiful Atlantic Ocean, there's a distinctive boundary that exists between the liquid ocean and the gaseous atmosphere. That distinctive boundary is not quite as distinct as you might think, because gases are exchanged between the atmosphere and the oceans all the time. So within the oceans, some of our primary gases include nitrogen and oxygen, just like we have in our atmosphere. There's also an excessive abundance of carbon dioxide. And yes, thanks to global warming, climate change, as we put more CO2 in the atmosphere, we tend to see more dissolution of carbon dioxide within ocean water. That's leading to some environmental difficulties. But these are your big three, the big 3 gases that we see in the oceans. So the next time you're at the beach, and I don't really expect you guys to do this, but if you think about it, when you're looking out over the beautiful ocean, realize that that barrier that exists between the liquid ocean and the gaseous atmosphere is not as distinct as you think, because gases are transferred between the two all the time, all of them. Just a little bit of ocean structure. There are a number of ways of actually defining the structure of the ocean. I tend to look primarily at more of the physical characteristics, but most oceanographers will also look at the environment as a whole, including biological organisms. When we look at the ocean structure, we can actually its physical characteristics in three main zones. The first, we simply refer to as the shallow surface mixing zone. This is the part of the ocean that we know the most about. Any type of documentary, movie, TV show that you see that shows fish, whales, sharks swimming in the ocean, and the water looks very bright and the sun is shining through and you can see things very clearly, that's the shallow surface mixing zone. Surface water is fairly warm, of course it's near the surface, gets a lot of radiation from the sun. Good sunlight penetration, you can see things very clearly, right? Fish, crabs, whatever, walk around. Also includes about 90% of all ocean life. Most ocean life is found in the shallow surface mixing zone. But surprisingly enough, that part of the ocean that we know the most about accounts for only 2% of all ocean water. That's it, 2%. So it's astounding. That which we think we know about the oceans makes up, as a whole, a very small percentage of the oceans themselves. I think that's, I guess, a tuna, but just to kind of show you an example. I gotta be honest, I was not able to find the best pictures of these things, but you know, do what we can. As we go a little bit deeper, the shallow surface mixing zone goes down to, it can vary. In the summertime, when the sunlight penetrates a little bit deeper, the depth can be to about 1,500 feet. In the wintertime, when the sunlight doesn't penetrate quite as deep, you can get to about 800 feet. So you could say on average about 1,000 feet is fine. Once we get below that, we come to the transition zone. In the transition zone, there's a very dramatic decrease in temperature, and I mean dramatic. All of a sudden, the water, which is nice and warm up near the surface, gets colder as we go deeper into the subsurface. We do see some sunlight penetration. This, in biologic circles or more environmental circles, we often refer to as the mesopelagic zone. Also, and I like this term myself, known as the twilight zone, because there's less sunlight and it's getting a little dimmer, duskier, a little creepy perhaps. You can still see things swimming around, but it's not nearly as clear or as bright as the surface zone. And this accounts for about 18% of all ocean water. This depth goes down to right around 3,300 feet beneath the surface. And surprisingly enough, has waves. Again, another realization, an astounding realization of the oceans. Now we know that the ocean has waves. You go to the ocean, go to the shore, excuse me, and you can see waves bobbing on the surface. Those are not the only waves that the ocean has. The ocean also has waves in the internal part of the ocean. So here, in the transition zone, where we see a difference in temperature, we're also seeing a difference in density of two water bodies. We have relatively low dense water near the surface, higher density water in the subsurface. And the fact that we have water of two different densities means that you actually have what may be regarded as two different water types flowing against each other. And that can produce a series of waves. So you couldn't really, it's hard to visualize, and if you were in the subsurface, you couldn't actually see it, but you might actually be able to feel it. This animation that you see here, which I know is not coming across too well, kind of shows this wave action within the subsurface. And that's actually what you would witness with these internal waves. So the boundary between the shallow surface mixed zone and the transition zone also gives us this wavy undulating pattern, which is reminiscent of waves that you might see on the surface. And again, the primary difference is simply the difference in density of the two different water bodies. The waves in the subsurface, however, can be big. I mean big. Some of the waves could be actually several hundred meters in height. I mean, they could be just enormous. But again, you wouldn't actually see them like you would see on the surface. They're just these very large undulations between these water bodies in the subsurface of the ocean. Right? Internal waves of the ocean. Who knew? Now we do. Now, once we go deeper into the ocean, we come to the deep zone. Now, as you can imagine, the deep zone, kind of hard to find a decent picture of the deep zone. Actually, I think the picture I showed you early on is probably the best one. Here in the deep zone, the water temperature is just above freezing. Water is absolutely frigid. And there's no sunlight penetration at all. No sunlight gets down here whatsoever. It is completely and utterly dark. So this picture that I have here obviously is illuminated by a submersible. It kind of shows you a bit of the ocean before, but if you look at the top, you can see how starkly, what a stark black light there actually is. And this accounts for about 80% of all ocean water, the deep zone, 80% of all ocean water. So this kind of gives us a nice little introduction to the basic structure of the oceans themselves. And this is a nice little diagram that I managed to pull up that kind of shows us the basic structure of the oceans themselves. Here's the equator, Mercury's latitude. Head to the left, go to the north, right on the south. And here we have our shallow surface mix zone, our transition zone, and our deep zone. Now, one of the questions that I'm commonly asked in my classes, because I can talk about this in my classes, is what's going on here? Why are the shallow surface mix zone and the transition zone extended all the way to the north to the south? Well, remember, these layers are identified based upon changes in temperature. When you get to your polar areas, there's not a difference in temperature. Water temperature at the depth is very cold. Water temperature at the surface also very cold. So there's really no way to differentiate these layers based upon temperature like we can in our low to mid latitude regions. At our poles, oceanographers just don't know what to do because there's no way to identify these layers, so they just draw the deep zone coming up to the surface. So a nice, simple idea of the structure of our ocean. The ocean, of course, is fluid. We know that. That's pretty obvious. And being a fluid flows from place to place. And that kind of introduces another component of the oceans, which we refer to as currents. Currents can be seen as these seams of water that flow throughout the oceans. I liken them, and I don't know if this is an analogy or not, maybe I hope it is, I kind of liken them to streams or rivers flowing on the surface. Because when you look at a river or a stream flowing on the surface, you're looking at a fairly narrow, linear body of water flowing from one place to another. That's almost exactly what a current is. It just so happens to be in the oceans themselves. So almost these stream-like movements across the oceans. Now, I have to tell you that understanding currents is very complex. There's a lot of them. The current motion in the oceans is vast and it's extremely complex. So the currents that we look at are going to be scaled down a little bit, just kind of give you an idea about what type of currents that we actually have. So this is a diagram I commonly show in my classes, which shows us our main currents across the globe. So of course we have our continents, and of course we have our main oceans. Now, each of our oceans is dominated by a feature known as a gyre. A gyre is a large circular current moving across the oceans themselves. So in the South Atlantic, we have the South Atlantic gyre, we have the North Atlantic gyre, and the Pacific, and so on. The blue lines represent cold water currents, the red lines represent warm water currents. And we can kind of get a sense of the circulation of water throughout each of the ocean basins themselves. The movement of oceans is largely dominated by a number of different factors. The first and foremost is wind. Wind is the dominant factor that governs the movement of currents. The movement of currents is actually very, very reminiscent of the movement of air in the atmosphere. Also the presence of land masses. You know, ocean currents can't flow through land masses, so when it hits a land mass, it's going to deviate or deflect. Variations in gravity, variations in friction, and always the term that I always have to test my students on when they've heard it before, the Coriolis effect. Ring a bell? Maybe what? Coriolis effect? Coriolis effect? Okay, well, Coriolis effect is it's a phenomenon that makes us realize that any free-flowing object on the surface of the Earth, as it travels across the surface, will be deflected in its original trajectory by the rotation of the Earth itself. So as the Earth rotates, and a free-flowing object moving across the surface is going to change its trajectory simply based upon the motion of the Earth itself. In the northern hemisphere, rotation is always to the right. Always to the right. In the southern hemisphere, it's always to the left. Always, 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 and always. Which is why when we look at our gyres in the southern hemisphere, they commonly flow in a counterclockwise direction. And in the northern hemisphere, they commonly flow in a clockwise direction. These are your gyres. This is just showing the dominant currents of the Earth. Let me rephrase that. The dominant superficial currents of the Earth. There are many, many other currents that are out there. Coupled with this, we also have a much larger movement of water that can be identified as the global conveyor belt. The global conveyor belt includes not just surface currents, but also deep water currents. It basically provides a large-scale movement of water across the ocean.
Yeah.
Thank you for that. So, the global circulation that we see here is a large-scale movement of water. And again, includes not just superficial water, but also deep water. And it almost represents blood flowing through a body. It represents the large-scale movement of water across each of the main oceans. And this is what's known as the global conveyor belt. The light orange areas represent surface currents, the blue represent cold, deep water currents. And we can actually see how the water flows, not just within the oceans themselves, but are actually part of a much larger circulatory system that covers all of our major oceans. Now, a couple of interesting facts about the global conveyor belt. One, it has a profound impact on the climate, which I'll talk about in just a little bit. But I do want to draw your attention to this area right up here. This landmass is Greenland. This landmass is Iceland. So this current, this profound Atlantic Ocean current flows between Iceland and Greenland. But allows us to represent, or allows us to realize a very distinctive feature. Now, one of the things I wanted to impress upon you during this lecture was how the oceans have a lot of amazing things, right? We were talking about new continents being revealed and waves, internal waves within the oceans. It also turns out that the oceans have waterfalls. And the area between Greenland and Iceland happens to be the location of the tallest waterfall on the planet. This is from Netherlands. And what you're looking at is the Denmark Cataract, Denmark Strait. And here we have warm surface water that flows to the north, but underneath that we have very cold, denser water that flows to the south. And it just so happens that as this cold, dense water flows to the south, it flows over this large land projection down to the bottom of the ocean floor. This represents natural waterfall on the ocean. But again, it doesn't look like the waterfall that you see here on the surface. The largest land-based waterfall we have is Angel Falls in Venezuela, about 3,000 meters high. This is 3 times as big. So it's enormous. So here you have this cold dense water that's flowing over this peak and then downward to the stick with the ocean floor. But it is technically a waterfall. And it happens to be the largest waterfall on the planet. It also just happens to be at the bottom of the ocean. So, and like I said, it's about 3 times as high as the largest land-based waterfall. So it's big, it's enormous. So here we realize that the ocean has waves in its internal body. It has continents that's revealed. We have new oceans that are being revealed. And lo and behold, we've identified the largest waterfall on the planet, which again is at the bottom of the ocean floor. But there's something else also. Another realization that oceans have that a lot of people may or may not realize that are actually out there. And that's this feature right here. Do you know what this feature is? I'm just taking a shot. It's not a barrier reef. That's a good answer. It's not quite a barrier reef. It's actually much too deep to be a reef structure. This feature, specifically on the left, is a lake. It's a natural fortified lake. Now, what happens is water from that's within the rocks on the bottom of the ocean floor can actually seep upward into the oceans. And when they do, they can dissolve salt that may or may not accumulate at the surface. So when that salt dissolves in the water that's seeping upward into the ocean floor, it makes the water very dense. Salinity always increases water. So as that water is dissolving the salt that may accumulate on the ocean floor, it makes that water that much denser and causes the surface to collapse in a way. As that salt is being absorbed, it forms a depression on the surface, and we see this large lake area feature. It is a natural lake, because the water body that we see here is far more saline than the rest of the water in this picture. It's a natural saltwater lake. And what we realized is, on the surface of this underwater lake, we also have waves, just like we have in the transition zone. And we have a shoreline that separates this lake feature from the rest of the ocean floor. You guys don't believe me? It's true. I looked it up. I verified it. It's true, right?
Where is it?
They're scattered at various locations. Usually there are places where salt content is a little bit higher. Usually around the equator.
There's more than one.
Oh yeah, all over the place.
There's lakes everywhere.
They can range from several feet across to a couple miles.
What's on the right-hand side, all the Is it yellowy? Yeah, what's that stuff?
Mussels.
Oh.
Mussels. Because mussels accumulate here on this shoreline feature, and they basically thrive on various nutrients that are found at the bottom of the ocean floor. So yeah, it's amazing. So the oceans have lakes, they have waterfalls, they have underwater waves, they're revealing continents, and that's one of the things I love about the oceans is here we think we know so much about the planet, and we do, don't get me wrong, we know a lot about the Earth, we know a lot about the atmosphere, but the oceans is still a place where we're just making these dramatic realizations about the world. And it's just phenomenal. It amazes me all the time. All the time. Okay, so why do the oceans matter? Well, the oceans cover about 70% of the surface of the Earth. Right? All right, so that's important. If we want to get around from place to place, we know people have been traveling across the oceans for thousands of years. Most trade takes place over the seas. Most international trade, I should say, takes place over the oceans. About 90% of all international trade takes place over the oceans. Most of the largest cities here lie near the oceans. Right? Think about it. Here in the United States, we have New York, we have Austin, we have Miami, we have LA, we have San Francisco, Seattle. All these major cities lie near the oceans because people live near the oceans. And about 40% of the world's population lies within 6 miles of the ocean. I know, it's amazing. So people have a very direct, very deep connection with the oceans. I don't think we realize how deep this connection is, or I don't even think we understand it, but the certainly is there because we are just drawn to the oceans. I mean, think about it. Every summer that comes by, oh, I'm going to go on vacation for a couple of weeks. Where are you going to go? I'm going to go down to the shore. I'm going to go to the beach. I'm going to go to the coast, right? We're just drawn to the oceans. There's something about it. Plus, we have a vast amount of resources at the oceans. There's a lot of fish and shellfish in the oceans. So there's a lot we can glean from it. And yet, surprisingly, we are still learning more and more about the oceans. All oceans are home to about 50 to 80% of all wetlands. A lot, right? As a matter of fact, it's quite certain that most oceanographers believe that there's a wealth of species within the oceans that have yet to be identified. We just haven't seen them yet. But every time we go down there, especially for our deeper depths, they're everywhere. The global conveyor belt provides upwelling. Upwelling is a process where cold, dense water actually rises further up to the surface, and when that happens, it brings with it essential nutrients from the ocean floor out to higher elevations, and basically forms the basis of the food chain. I think this, I apologize to my biologist audience, but I think the food chain is outdated, right? It's like a food web, I suppose. So,
Yeah.
sorry about that.
Sorry.
You can tell I'm not a biologist at all.
We'll talk after your question.
Yeah, okay, I'm trying to answer. And like I just said, the resources that we get from the oceans, fish, shellfish, and of course, certain cultures are dominated by these foodstuffs, like some Asian cultures, the Japanese, Koreans. I mean, their diet is largely based on stuff from the oceans. We get a lot of energy in the oceans. When we looked at the continental shelf a short while ago, we know that we've acquired vast amounts of resources. We have sand and gravel that's used in construction. Certain heavy metals can be recovered from the oceans. And petroleum. So we have these oil rigs which line our continental shelves, primarily along the Gulf Coast and on the northern coast of Alaska, whose primary function is to extract petroleum. And there's a lot of petroleum that's out there. It's a lot of it. But fortunately for us, we're also looking at alternative sources of energy. And the oceans, being so wide, open, and vast, allow a fantastic opportunity for winds to blow. Winds can blow extremely fast over the ocean, and they can blow freely over the oceans, and that aids in the driving of these wind turbines, which again help produce energy in an alternative fashion. Algae and phytoplankton have been producing oxygen for millions of years. Surprising fact for you. These single-cell bacteria, these single-cell plankton in the ocean, through the process of photosynthesis, have produced an extraordinary amount of oxygen across the atmosphere. About 70% of all the oxygen we breathe comes from the oceans. I mean, we know about plants, we know about grass and trees and leaves and all. That makes up about 20 to 30%. But ironically enough, most of the oxygen that we breathe in the atmosphere comes from the oceans. Nice little addition here. I wanted to include this because as a teacher, I'm always trying to encourage people to get into science and trying to stimulate them and interest them in the wonders of the earth itself. And the oceans do just that. I mean, the oceans are the one place, I shouldn't say the one place, but a prime place where exploration, new discoveries, new realizations are happening all the time. And it can generate younger generations and older generations to get excited about science. Now, no disrespect to NASA whatsoever, but when we send a probe out into space to check out Mars or Saturn or one of these other planets, it takes a long time. New Horizons spacecraft took 10 years to get to Pluto, 10 years. That's a lot of time to wait to see what secrets Pluto has. Here, the oceans are right here in our backyard. We can explore them right away, and we can really kind of drive interest in STEM and scientific discovery in a fairly quick and efficient manner. And of course, oceans do have a regulation of climate. Thanks to that global circulation, that global conveyor belt, the oceans are huge repositories of heat energy. And they're able to transport heat energy from the tropics to the poles and help in diffusing heat energy across the planet. And without the global conveyor belt, the tropics would be far, far hotter, and the poles would be far, far colder. It would be a very different world that we live in. Now, the oceans are not just responsible for climate across the entire planet, but also localized climate. The oceans play a crucial role in affecting local climates, and one of the best examples of that is Europe. And a large part of that is thanks to this famous American. And friend. Bear with me. I'll make the connection, I promise you. Ben Franklin was an amazing American, right? He had many different roles. He was a statesman, he was an ambassador, he was an inventor, he was a printer, he did all sorts of amazing things. One of his earliest jobs here in the early American colonies was the first Postmaster General of the United States. He handled all the mail coming to and from the American colonies. And being the first Postmaster General of the United States, he had realized that when ships carrying mail went from the American colonies to Britain, they moved at a pretty good clip, pretty fast pace. But when ships traveling with mail went from Britain back to the American colonies, they took more time. They traveled a bit slower. Ben Franklin wanted to know why. Why is it that ships going from America to Britain travel much faster, and ships traveling from Britain to the US travel much slower? He realized, or he rationalized, that there must be some type of force that ships are fighting against coming back to America. And he was right on. He was spot on. And he was first credited with mapping the Gulf Stream current right off the eastern coast of the United States. That's a picture of his early map. Here we have Florida, the Carolinas, Virginia, New Jersey, somewhere up in there. That's the Gulf Stream current. Gulf Stream current is a very powerful warm current that flows northward along the eastern seaboard of the United States. And Franklin was the first to recognize it back in 1769, if I'm not mistaken. And he was absolutely right. So, what is up with this Gulf Stream current? The Gulf Stream current is a warm water current and does affect localized climates. Now, around the mid-Atlantic region, the Gulf Stream current deviates and moves out to the North Atlantic and becomes what's called the North Atlantic drift current. And traveling across the North Atlantic hits mainland Europe pretty much square on. Britain, France, Germany, even southern parts of Scandinavia, southern Norway, southern Sweden. And thanks to this warm water current, which brings with it relatively warm conditions, these areas, which are fairly high line of latitude, enjoy a nice mild climate. Many people think that, oh, I'm going to hop a flight in Philadelphia, I'm going to fly directly east, right along the same line of latitude across the Atlantic Ocean, and I'm going to land in Heathrow, Portland. I don't think so. If you travel from Philadelphia directly east across the Atlantic, you're going to wind up in Portugal. Most of mainland Europe actually lies on a much higher line of latitude, pretty much central Canada. Yet we know here central Canada is very cold, and yet Europe enjoys a fairly nice mild climate. A large part thanks to this Gulf Stream current. Ironically, the Gulf Stream current, which like I said is a warm water current, hits southern Iceland, again, with Britain, and makes Iceland fairly nice and mild. Greenland, however, completely misses that Gulf Stream current and stays mostly ice. So Greenland happens to be mostly ice, and Iceland, ironically, is mostly Britain. So this is just one example. This is an example I commonly use to show how ocean currents can most definitively affect climates. We are also affected by this Gulf Stream climate here in New Jersey. And although it hasn't been officially designated, this may also help us understand why hurricanes and tropical storms, as they travel up the eastern seaboard, can last a little bit longer because they can feed off that warm water of the Gulf Stream current. And, again, this hasn't been officially designated, but it certainly is a decent proposition. This may also explain the occurrence of shark sightings across the eastern seaboard, because sharks love warm water. And so sharks have been found at fairly high lines of latitude, thanks in large part to this current, or so we think. So every current that's out there that lies near landmass certainly has an influence on the climate of that landmass in some way. There are other things that come into play. I'm not saying it's just based on these currents. There are other factors that come into play, but current mostly is a factor. As far as ocean issues go, a little bit on ocean issues. I think you probably realized what wasn't in Marc already. Pollution. I mean, obviously, this is a pretty obvious statement. About 80% of all ocean pollution originates from land. It comes from everywhere. Mostly non-point source pollution, which is just basically one-off, all sorts of garbage and contaminants and pollutants leaking from the surface of the earth into our oceans. Plastics make up a large percentage of this space. Plastics, we think they're fantastic because plastics are cheap. They last a long time. We can mold them into all sorts of shapes, whatever we want. But man, they wreak havoc on the environment. And when plastics get into the ocean, they're there for a long, long time. We are dealing with plastics right now. You may have heard news reports about microplastics being found everywhere. Microplastics, tiny little bits of plastics are found just about everywhere. Point Nemo, plastics. Microplastics primarily, but plastics are in Point Nemo. Also, a feature known as the Challenger Deep, the deepest part of the ocean, about 32,000 feet beneath the surface of the ocean. Last time they explored down the Challenger Deep, plastics. Plastics everywhere. It's horrific, it really is. And you may have heard stories about these garbage patches that we see across the planet. Yeah, we do see those. I had mentioned before these gyres, these large-scale circular rotations of water across the ocean basins. Ironically, in the middle of these gyres, water is fairly stable. It doesn't move a whole lot. It's in these relatively stable parts of the oceans where a lot of our plastics, our garbage, and our junk pretty much accumulates. And this map kind of shows us where a lot of this stuff is. This area right here is the Sargasso Sea, right off the eastern seaboard. A large number of plastics accumulating here. Now keep in mind, these garbage patches are not like little patches of garbage all floating together. In many cases, they're interspersed, they're distributed, and in many cases include a large amount of microplastics, things that are very difficult to see. But nevertheless, we do see abundance of these materials at certain spots across the oceans. And of course, that has a profound impact on ecosystems and, of course, marine life, just a horrible, horrible effect. As far as cleanup, as far as I know, last I checked, there really isn't any reasonable way to clean this stuff up right now. Because we could go out there and we could skim some of the larger stuff off the surface of the ocean. But like I said, because the oceans are so large, and because we're contributing so much waste to the oceans, we would hardly make it down. So we really need to come up with some way to get this stuff out of the oceans, especially microplastics. That's a whole other issue altogether, because these things are tiny, right? You can't really see them, but they're everywhere. Changes in heat, decrease in global temperatures due to climate changes causing the global conveyor belt to slow down. I showed you that large circulation of water, both shallow and deep marine currents. That helps regulate climate across the planet, but oceanographers do know that that global conveyor belt is slowing down. And the fact that it's slowing down is believed to wreak havoc on some of our weather systems. Increased number of storms, severity storms, droughts, heat waves, blizzards, who knows? We haven't made that connection just yet, but there's a very strong connection between the two. Now, this global conveyor belt is slowing down. What happens if it stops? We don't really know. Right now, oceanographers estimate that it takes about 1,000 years for a drop of water to travel that entire circuitous route along the global conveyor belt. But if this circulation slows down further or even stops, it's a big question mark as far as how that's going to affect life on the surface. We also know that the ocean is getting more and more acidic. This is a graph I pulled from NOAA. I'm not going to go into a lot of detail, but this blue line here shows us how the water of the oceans is actually becoming more and more acidic. And again, this can have a profound impact on animals. especially animals who generate calcium carbonate, CaCO3 for shells or hard parts. It's having a very destructive effect. That includes corals, by the way. Overfishing, again, our vast hunger for seafood and fish and shellfish is causing a dramatic depletion of these organisms. We're trying to come up with some way to regulate the fishing industry and have it where we can pull fish out of the oceans, but do it in a very sustainable manner. It's a very awkward process. We have made some great strides, but there's a long way that we have to go still. But even now, we just pull fish out of the oceans like crazy. And it's amazing because a lot of the fish that we pull out, we don't necessarily want or need. They are an essential part of the environment, essential part of the food chain, but this bycatch that we pull out of the oceans, which is now turned into waste, again, has an impact on the environment itself. And as we see more and more coastal development, of course, that's going to lead to more and more waste that's going to drain from our land into the oceans. And you can't deny that the presence of humans on the coast most definitely has a significant impact on the oceans themselves. So just a quick summary. The oceans continue to force people to revise their perception of the world. We have new oceans that we have discovered. We have new continents that we think we've discovered. So the oceans are revealing a vast array of secrets, things that we could not even dream of before. And the oceans themselves have some pretty amazing features. We have rivers in the ocean. Those are your currents. We have waves within the ocean, not even on the ocean, but inside the ocean. And we had talked about these brine lakes, or these saline lakes that we see in the oceans as well. The oceans represent the last truly unexplored part of the Earth. That's without saying, right? The Earth we know a good amount about. The atmosphere we know a lot about. The oceans, we still have a lot to learn. As human population grows, we do have a deep necessity for the oceans. Like I said, there's a deep connection between people and the oceans. We use the oceans for food, and sadly, waste disposal. Waste disposal is a big problem. We have, over 7 billion people on the planet producing waste like crazy. And no offense here, but those in more developed nations produce even more waste than almost anybody else. And a lot of this waste ends up in the oceans in one form or another. Something has to change. It's got to. And obviously there exists a direct connection between life on land and the oceans. And the health of the oceans is probably the best representation of the overall health of the planet itself. So I covered quite a bit of information here. I know there's a lot more that we could cover, and I didn't get into shoreline features or the Challenger deepening type of detail, or even ocean floor features, but that's what I have for you, and I'll be happy to answer any questions at this time.
I think you explained it, I didn't really understand. Define a new continent.
In most cases, well, first off, we don't really know how to define a new continent, but the continents that I showed you before are defined mostly based upon composition. The ocean floor, no matter what ocean you're looking at, Pacific, Atlantic, Indian, the ocean floor is really defined by a type of rock called basalt. Continental rock is made up of all different types of rock, but is generally defined as being granitic, or a granite type of rock. So those land masses that we see in the ocean that might be continents have a composition that are more akin or more similar to continent land masses than the basalt in the ocean. So it's really based largely on composition.
I got you, thank you.
Sure.
So you had mentioned that we haven't really explored a lot of the ocean. Is there a certain reason why? Is it just because we don't have the equipment? We know that like James Cameron, they had a certain submarine, if you will, to look at the Titanic, but can we not, is it just the time, is it the equipment? Why have we not explored more?
In most cases, funding. It just costs money. We have submersibles that can make it down to the ocean floor, but remember, as you go to the ocean floor, water temperature decreases dramatically, but pressure increases dramatically. And even our nuclear submarines can get down to the ocean floor because they'd be crushed by the massive pressure. Across the entire planet, we have about five submersibles that can handle the pressure of the ocean floor for the entire planet. That's not a lot. And keep in mind how large the oceans actually are. So we have 5 submersibles, and because of the size of the oceans, we're inching along, doing a little bit at a time. But in terms of why don't we know one more, it's largely based upon hunting. Now, the maps of the ocean floor that you may have seen that show different features of the ocean floor, a large part of that is extrapolation. So we can make very detailed maps of the ocean floor using a process called bathymetry, similar to sonar. We can make very detailed maps of the certain parts of the ocean floor, and then we just kind of extrapolate to the surrounding area as far as, well, we think this feature extends out this direction, this feature extends over here. And from that, we can actually produce maps of the ocean floor that we see today. Good question. Yeah.
Who owns these submarines that go to the ocean for submarines?
I know the U.S. has a couple. The United States has a couple. You may have heard of Alvin. I think Alvin is the most popular one. I'm not sure who owns the other two. Maybe the Europeans, the Japanese. I'm not really sure. But I know the U.S. has at least a couple.
What's the relationship between the gyre, the Gulf Stream, and the conveyor belt? Are they all kind of part of the same big picture?
They are. Let me just pull up my gyres here. And like I said, when we talk about ocean currents, it does get very complex. But when we look at our gyres, these are superficial currents. So our gyres represent largely superficial currents. The global conveyor belt includes not just surface currents, but also deep currents. So when we look at the North Atlantic here, we have this gyre that moves in a clockwise fashion. But you have to kind of think three-dimensionally. And as this water moves around in a clockwise fashion, when it gets up to the north and that water begins to cool, it's going to get heavier. And as it gets heavier, it gets denser and begins to sink down into the ocean floor. So while we have this movement across the surface, at the same time, we also have water moving in the subsurface at deeper depths, which obviously is very hard to visualize on that image. So we have the movement of the gyres that are coupled with this global conveyor belt. They're kind of moving in concert with each other.
In the Gulf Stream? Or is that?
The Gulf Stream is part of this gyre, the North Atlantic gyre. So I guess the short end of the question is, your gyres are largely superficial currents, water moving across the surface. The global conveyor belt includes not just surface currents, but also deep water currents, which are not visualized here.
The West Coast is actually a colder ocean than,
Yep.
I mean, for going swimming and all that.
Yeah, that's because of the California current, which is as you can see here, a cold water current. That also explains why, when you look at California, you have much more cooler conditions than you have here on the east. For example, San Francisco. Anyone who's been to San Francisco or parts of the Pacific Northwest, there's a lot of clouds, there's a lot of fog, and the temperatures there not really too hot. I mean, it's fairly moderate, thanks in part to that California current, which is a cold water current. So the cold water of this California current does have an impact on the superficial conditions around the coast of California and the rest of the Pacific Northwest. Yeah.
When they do long-term weather forecasting, they always talk about El Nino and that. Could you briefly explain what that is?
El Nino.
I mean, it has to do with the ocean, right?
Of course it does. And, okay. El Nino, it's just time. All right, so El Nino. El Nino is the shifting in water currents and wind currents across the Pacific Ocean. Now, what we typically see is this. The Peru current moves northward off the coast of South America. And, like I said, we have this process called upwelling, where we have water rising, it's moving from a fairly deep condition up to the surface, and then moves across the Pacific Ocean. When this happens, like I said, upwelling allows us to bring essential nutrients to the surface of the ocean. It helps kind of continue the food chain, the food web. And that's why fishermen off Ecuador, Peru, Chile, they really like that upwelling because it supports a lot of the fish life that we see off the coast. Now, once this water hits the surface, it warms and it moves across the Pacific over to Australia. Now, in the case of El Nino, there's something that happens where there's a shift, and the warm water that we see in the western part of the Pacific actually begins to grow and encroach further and further to the east. And it encroaches so much that this cold water current that moves up the the western seaboard of South America is hindered. So we don't see as much upwelling, And the fishing industry really takes a hit when El Nino actually happens. We don't know why this happens. We do know it happens, but we don't know why. So basically what El Nino is the expansion of this very warm water from the western Pacific further to the eastern Pacific. And that kind of impacts a lot of your localized currents off of South America. Ironically, this happens typically around December, around Christmas time, which is why El Nino was referred to as the child, because child, Jesus Christ, Christmas time. And it's just kind of ironic that it's a negative impact on the fishing industry of South America. But after a few weeks, the system kind of restarts itself, and this patch of warm water across the surface moves back to where it belongs, and this upwelling is allowed to resume. So that's essentially what El Nino actually is. And like I said, we don't really know why it happens, but we do know it happens.
But this doesn't happen every year.
No, it doesn't happen every year. It happens every few years.
It affects California.
Yeah. Oh yeah, well actually it affects weather in many different places, especially California. One of the positive aspects about El Nino, based upon meteorological research, is during El Nino events, there's a significant decrease in storms, tropical storms, and hurricanes in the Atlantic Ocean. So yay for us, we get to benefit from that. But there's also an increase in droughts in parts of the Southwest. You have increases in rainfall, and I mean torrential, monsoon-type rains. Here in the West, the weather conditions are just severely affected. But again, we know pretty much what happens, but we don't know why it happens. That's the big question. I like this diagram because it kind of shows us a nice simple array of movement of currents, but like I said, when you look at currents, it gets very complex, and there's a lot to it. Even the currents that we see here represent just the smallest fraction of all the currents that are out there. They're just everywhere. And of course, El Nino was a representation of that. So, yeah.
The current that's really deep, that does the whole flow, you said it takes one drop of water, did you say 1,000 years to go? Is that
About
right?
that.
1,000 years for one drop of water to do the whole circle. That just seems unbelievable.
I know. Yeah. Well, of course, it's based upon measurements of the movement of the currents. Yeah.
So the deeper they're going, are going slower than the ones on top?
Yeah. The surface currents typically go much faster because currents are largely produced by the movement of winds, and winds, of course, happen at the surface. But as that water is pushed across the surface, friction also pulls deeper water with it as well. Oh,
You didn't touch much on rising ocean level. Is that something we need to worry about?
yeah, it did touch. All right, I'll touch on it right now. Sorry, Lorraine. This will take 2 seconds. All right, let me pull this slide right here. Changes in heat. A lot of people associate rising sea levels with melting ice caps, which of course is an issue. A lot of people realize that when material is heated, it has a tendency to expand, and that's very true for the oceans. So as ocean water actually increases in temperature, it's going to behave like any other type of medium, but will actually expand. This is going to also exacerbate the whole rising sea level issue, and we are seeing that take place right now. Sorry, there it is. Yeah.
Are you optimistic about the health of the oceans, that we as humans are ever going to do anything to take it seriously, whether it's overfishing, whether it's the plastics, whether it's the population going to 8 and 10 billion in 2050? What is your, I mean, is extinction just built into?
Well, am I optimistic in the short term? No, not at all. Nothing's going to happen. Nothing's going to change. But the way I look at it is, I don't like to be too pessimistic. Despite me being a scientist and a cynic, I try not to be too pessimistic. When change happens, it can happen in a couple of ways. You can either choose to make a change, or you are forced to make a change. Right now, we're still in a position where we can actually choose to make a change for the better. And we're enjoying that. That's not going to last forever. Eventually, there will come a time when we are going to have to make a change. And when that happens, our choices typically are far more limited and far more extreme. So, we're not going to go extinct over this. We're not going to, I hope, suffer egregiously, but most certainly there will be some changes that have to take place in some form or another.
also teach here as a scientist. I teach ecology, and this is something we talk a lot about in ecology as well. I am hopeful in the students that we teach. I have so many students who are interested in the oceans, interested in cleanup conservation, looking at solutions to the problems. I'm not necessarily hopeful in people who are far into their adulthood, because maybe we have already started a pathway and are stuck in some of our decision making. Some of us are learning and interested. If you're here, that's fantastic. It shows that you're interested in learning. But when my students are very interested in starting a new pathway, and I think that that is something that gives me hope, that it isn't that that everybody is relying on convenience and things. But like we talk a lot about the islands of trash and microplastics and how plastics don't degrade and break down, but they just break into little pieces, and how do you deal with that? And even space trash and things. We talk about all the issues, and I'm hopeful because they're looking for solutions, and that's something that I think is that's where my hope is.
I think there's a very definitive link that needs to occur, and I'm hoping that Anne's students, maybe even my students, can actually do this, where in terms of the science and the environmental conservation, the desire is there, and like Anne's students, the students want to see change, they want to be proactive, but there's a disconnect between the scientific community and the political administration. I mean, bear with me here. And I'm not saying that scientists have to go and be antagonistic, and we have to be critical, and we have to be very mean about it, but there has to be an understanding between the political administration and the scientific community. They have to work together. They have to, because you can have any number of scientists screaming and yelling and saying, "Oh, we got to make this change. We got to do this. We got to do that." But unless they work in concert with the political administrators, I don't see a lot getting changed. So if it's a matter of educating the politicians that may come to it, may come to, like I said, being forced to make a change, we have to work together. We cannot be butting heads, we cannot be mean or antagonistic, we have to work together. That's the only way we're going to get through this. So like Anne, I think there's a definite pathway that our students can actually benefit from, not just learning the science behind it, but also learning how to go into a political environment and make a change in that area. That's my thought.
Speaking of educating politicians, that's one of the reasons we have My Science Matters, right? Because everybody, scientists or not, need to have some basic understanding. And I think that this lecture, amazingly, so enlightening, really leads us to ask you to come back again, because there's so much that you haven't talked about. And he's giving us lots of fodder to impress our friends at the next conference.